Swayam Prabha. Digital India. Educated India.
Let us do something very simple, and once again what we will do is we will work out the easy ones here. I will give you a little bit of difficult one to do at home, and next Friday we start with this. Okay. What we said, if you remember, is that whatever we have discussed so far is in the language of geometry. But then if you really want to work out a methodology by which you can do things very simply, or maybe let a computer do it, then the only way in which that is going to happen is if you translate all this into the language of algebra. And we perform this translation from geometry to algebra by using our familiar friends, matrices. Okay. What are matrices? Matrices are just arrays of numbers, isn't it? So let us see how that happens. So let us say I am talking about a transformation of a point with coordinates x, y, z. Okay, x, y, z. So identity matrix is very easy to work out. It is actually the identity matrix, unit 3 by 3 matrix. Because if you perform C1 or E, then what happens to x, y, z is that the x remains x, y remains y, z remains z. No change. So the transformation matrix is going to be 1 0 0 0 1 0 0 0 1. Okay. Now let us think of reflection, and to keep things simple, let us talk about x, y, y, z and zx. Okay. What happens when you perform reflection with respect to, say, xy plane? What happens to x? What happens to y? What happens to z? X remains same, y remains same. What about z? Z becomes minus z. I think we all understand that. Okay. So x remains x, y remains y, z remains z. Z becomes minus z. Sorry. Okay. What will be the matrix? Now it's child's play for you. 1 0 0, then right. Okay, 1 0 0 0 1 0 0 0 minus 1. This is the matrix. So what have we got? We have got the matrix representation of reflection with respect to xy plane. Okay, very simple, no difficulty so far. Now tell me, what will be the matrix? What will the matrix be for yz? For yz, again y and z will remain the same. So x will change sign, x becomes minus x, right? So minus 1 0 0 0 1 0 0 0 minus 1 0 0 1, sorry, and zx, yes. Okay. Now before going any further, let me state something that is perhaps obvious. I would like to draw your attention to these elements here, because that is something that comes handy later on. Diagonal elements and off diagonal elements. What is the meaning of diagonal elements? What is the meaning of off diagonal elements? That is what I want to ask you. See, on the right hand side, what do we have? We have the transformed coordinates, isn't it? Right? And what is this? This column here? That is the original coordinates. Each element of the matrix basically gives us the contribution of one of the original coordinates in each of the transformed coordinates. Did I put that in a very complicated manner? Okay. Look at this first one, the 1 1 element. Where did it go? The 1 1 element here. This multiplied by x will come here, isn't it? So what is this x? This x is basically 1 multiplied by x plus 0 multiplied by y plus 0 multiplied by z. Okay. So, this 1 1 element in the transformation matrix tells us about the contribution of the original first element in the transformed first element. Make sense? Dola? Make sense? Not scary? Very good. What about the second one? The problem is here it is 0, but still let us think, if it was non-zero, what would it have meant? Contribution of original y in transformed x, right? What is this, 1 2 or 2 1? What do you call it? What is the element number? 1 2, right? Row number, column number. Row number first, column number second. So, the 1 2 element stands for the contribution of the second original coordinate in the first transformed coordinate. Okay. What about this 0 here? 1 3. It stands for the contribution of z in transformed x, the contribution of the original third element in the transformed first element. Okay. Similarly, you can work out 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. So now if you focus on 1 1 element, 2 2 element and 3 3 element, the diagonal elements, won't you agree with me when I say that they stand for the contribution of a particular element in its transformed avatar? Is that so? What is 1 1? It is a contribution of x in x, contribution of original x in transformed x. What is this 2 2 element? Contribution of original y in transformed y. What is the 3 3 element? Contribution of original z in transformed z. Do you agree with me? Perhaps it's obvious to many of us, but in case it is not, I think I want to stress this point. It's important to understand what matrices mean. It's not just any array of number. Okay. So, diagonal elements stand for your contribution of an element in itself after transformation. Off diagonal elements stand for contribution of a coordinate in another transformed coordinate, isn't it? So, see here what has happened is that x, y and z have not mixed. They have either remained what they were, or at most they have changed sign. X and y have remained the same, z has changed sign, but there is no xy mixing. Okay. That is why you have a diagonalized matrix here. The transformation matrix is such that only the diagonal elements are non-zero. The off-diagonal elements are all 0. When you have a matrix like this, what it means physically is that there is no mixing of coordinates. X remains x or becomes minus x, y remains y or becomes minus y, z remains z or becomes minus z. But there is no mixing of x with y, y with z, z with x. Make sense? Huh? So, you see, identity, there is no question of mixing. Even deflection with these planes that we have taken, they do not cause mixing of coordinates. Fine? What about rotation? It's customary to take the z axis as the rotational axis, always, right? Z is always unique. Okay? So, if you turn with respect to z, then what will happen? To start with, I have written these as x1, y1, z1, the original coordinates, and x2, y2, z2, the transformed coordinates. Since z axis is the rotational axis, I think it is not very difficult to understand that z2 will just be equal to z1. Right? So, z does not mix with x or y, right? So, I can write a part of the matrix. Right? Z remains by itself, z is unique because you are performing a rotation with respect to z. So, I can actually fill in these elements here. This 3 3 element is going to be 1 and these off diagonal elements involving z. What is this? Contribution of what in what? Z1 in transformed X, X2, right. What is this? Contribution of Z1 in, yeah. What is this? X in Z. And second, this one is contribution of Y in Z. Okay. Since Z does not, there is such a snob that it does not mix with X and Y in this case, right? It likes to be by itself. So I can actually fill in all this. What is left is this block here. This 2 by 2 block is what I have to fill. Okay. And here you see, I cannot have something that is very simple. Because what has happened is, you have turned, now think of the projection of the position vector on xy plane. Okay. x1, y1 has become x2, y2. There is no way in which you can represent x2 just in term of x or y2 just in term of y, right? There is a mixing, because this point has x and y components, this point also has x and y components. Mixing is there. Okay. Can you work out the expression? Can you work out this expression? What is x2 equal to in terms of x1 and y1? What is y2 equal to in terms of x1 and y1? It is perhaps better to write. If you can work it out looking at the board, it will be great. It's not impossible. Okay, so it's obvious that people understand that it's got to do something with cos theta and sin theta, isn't it? That is very obvious. So I'll give you the answer, but please work it out. If you cannot, then we'll work this out in class next day. This is the answer. x1 cos theta minus y1 sin theta, and y2 is x1 sin theta plus y1 cos theta. So tell me what the matrix will be now. Cos theta minus sin theta and sin theta cos theta. This then is your transformation matrix. And this is the beginning of something important. Because you see, you can actually divide this matrix into two blocks. You can draw a line like this and you can draw a line like this. Because the story that this matrix tells us is that as a result of rotation with respect to z, what you have been able to do is that you have been able to create two different classes of coordinates. X and y mix with each other, right? So they give rise to this 2 by 2 block, and z remains what it was. So that gives rise to this 1 by 1 block. All these zeros are useless. So what I might as well do is I can draw a line like this and I can draw another line like this. So what I have essentially done is that I have divided the matrix into two parts, or as they are called, two blocks. A 2 by 2 block and a 1 by 1 block, which is just a number. Alright. This is the beginning of something that is going to be very useful for us later on. Okay. So please work this out by yourself. This is worked out in very nicely. Cotton's book is also there, but then Harris and Bertolucci's book is where it is worked out in all the detail. Okay. So we close here today, and next day what we do is we start from here, we talk about the transformation matrices, and then we take a little bit of mathematical interlude. Because what we need to do is we need to remind ourselves about the properties of matrices, and then we'll see that we'll use something called group theory. We are going to show you that all the symmetry operations form what is called a group. Are you familiar with the term group? Not political group or anything. Mathematical group. Are you familiar with the term group? What are the properties that the elements of a group have to satisfy? Not mention the obvious. First property is identity. Identity. Don't neglect the obvious. Okay. So we'll just remind ourselves of what are the properties of group, and then we are going to demonstrate that these symmetry operations actually form groups. Okay. And then a little bit of properties of matrices. From there we'll see how one can use group theory to arrive at something called great orthogonality theorem. And then comes the application part. Using great orthogonality theorem, we learn how to construct character tables, and then using character tables, we will construct symmetry adapted linear combinations. We'll see what they mean, and that is what will allow us to go into a description of molecular orbital theory from the point of view of symmetry. Okay.